Across decades of Antarctic research, scattered declassified documents describe patterns beneath the ice that refuse to settle into any single explanation. From seismic irregularities and magnetic instability to mapped voids that appear strangely interconnected, the records do not present a singular discovery, but a sequence of findings that begin to align in ways that were never intended to be read together. Within these files, the continent is not silent in the way it appears on the surface, but active in ways that challenge conventional geological understanding. In this investigation, we move through expedition logs, technical reports, and restricted analyses drawn from multiple scientific disciplines, tracing what researchers recorded beneath ice sheets, subglacial lakes, and deep ice bed interfaces across Antarctica. Each layer of data reveals measurements that should not converge, yet repeatedly do, forming a hidden continuity beneath the frozen landscape that raises a single unsettling question about what has been present there all along. The first declassified seismic anomaly. The document did not stand out at first. Buried among thousands of pages released through gradual declassification, its technical language and dense formatting resembling countless other Antarctic survey reports. Yet within its data tables and seismic interpretations lay a detail that resisted easy explanation. Subsurface readings that suggested vast hollow spaces extending far beneath the East Antarctic ice sheet. These were not small fractures or isolated cavities, but structures of unusual scale and continuity, recorded during geophysical surveys conducted across regions long believed to be geologically stable. The file, originating from Cold War-era seismic studies, was intended to map bedrock and ice thickness, but instead it revealed something that did not behave like either. During the mid-20th century, Antarctic exploration shifted from surface observation to subsurface analysis, driven by advancements in seismic-sounding techniques. By transmitting waves through the ice and measuring their reflections, scientists could estimate depth, density, and structural variation beneath the continent. This transition accelerated during the International Geophysical Year of 1957-1958, when coordinated scientific efforts expanded seismic surveys across previously uncharted sections of East Antarctica. In theory, the results should have aligned with established glaciological models: layered ice above solid bedrock, interrupted occasionally by subglacial lakes or sediment pockets. However, in several recorded instances, the returning signals behaved unpredictably, echoing in ways that implied open voids rather than compressed material. The anomalies were not uniform, but they shared a common characteristic. The waves appeared to travel through space before reflecting, suggesting the presence of cavities far larger than any previously documented. What made these findings more difficult to dismiss was their repetition across multiple surveys. Separate expeditions, using different equipment and conducted years apart, recorded similar distortions in seismic data across overlapping coordinates. In conventional geology, such consistency would indicate a persistent structural feature, yet no known natural process could easily account for voids of that scale beneath kilometers of ice. Early interpretations attempted to attribute the anomalies to instrumental error or interference within layered ice strata, where density variations can sometimes distort wave behavior. Others suggested the presence of subglacial sediment pockets or unusually shaped bedrock depressions. Yet each of these explanations began to erode under closer examination, as recalibrated instruments and repeated passes continued to produce nearly identical readings, reducing the likelihood that the anomalies were artifacts of equipment or isolated geological quirks. The report's language remained cautious, avoiding speculation while noting the limitations of interpretation. Terms like non-uniform voids and anomalous propagation zones appeared repeatedly, accompanied by diagrams that seemed to outline empty chambers embedded within the ice or just above the bedrock. In one section, the data suggested a vertical continuity between these spaces, implying that they were not isolated pockets, but part of a larger interconnected system. The possibility of subglacial channels was briefly acknowledged, yet the scale and geometry did not align with known hydrological processes, which tend to carve narrow, irregular paths rather than broad, stable cavities. As Antarctic research advanced, later discoveries provided context but not resolution. the identification of vast subglacial lakes, including those beneath regions of East Antarctica, confirmed that large bodies of water could exist undetected beneath the ice for millions of years. These lakes, sealed off from the surface, became subjects of intense scientific interest, particularly for their potential to harbour microbial life adapted to extreme isolation. Yet the formations described in the earlier seismic file did not match these environments. Where lakes presented smooth, consistent interfaces, the recorded anomalies suggested depth variations and internal complexity, as though the spaces themselves were structured rather than naturally pooled. Further examination of the declassified material reveals moments where the data seem to challenge the assumptions of the researchers themselves. In one segment, seismic waves appeared to weaken unexpectedly before returning with altered frequencies, a phenomenon not easily explained by space alone. Such behaviour hinted at something within the voids, something capable of absorbing or modifying the energy passing through it. While the report stops short of concluding, the irregularities were noted with enough concern to warrant additional survey passes over the same region, each confirming the presence of the anomaly without clarifying its nature. In at least one repeated pass, subtle variations in the return pattern suggested that the internal structure of the voids was not entirely consistent, as though the boundaries themselves were subject to change rather than remaining fixed over time. The geographical context deepens the unease surrounding these findings. The coordinates referenced in the file correspond to areas of East Antarctica where the ice sheet reaches extreme thickness, in some places exceeding 4 kilometers. Beneath such pressure, the existence of large, stable cavities becomes increasingly difficult to reconcile with known physics. Ice at those depths behaves plastically, slowly flowing and reshaping over time, which should collapse any open spaces unless supported by an internal force or structure. Yet the repeated detection of these voids suggests that they persisted despite conditions that should have erased them. In the decades following these surveys, technological improvements allowed for more precise imaging of Antarctica's subsurface. Radar sounding and satellite observations expanded the understanding of subglacial landscapes, revealing mountain ranges, valleys, and hidden lakes. However, the specific anomalies described in the earlier seismic file were rarely revisited in public literature, their coordinates appearing only in limited datasets or not at all. Whether this absence reflects a shift in interpretation or deliberate omission remains unclear, but it leaves the original findings suspended without resolution. What remains most striking is not a single data point, but the pattern that emerges when the file is read in full. Across multiple entries, the anomalies share a consistency that resists classification, appearing neither random nor easily attributable to error. The instruments used were calibrated against known conditions, and while early seismic techniques had limitations, the repetition of results across independent surveys reduces the likelihood of simple misreading. Instead, the data suggests the presence of something persistent beneath the ice, something occupying space where no conventional model predicts it should exist. The file concludes without a definitive explanation, its final sections shifting back to standard geological observations, as though the anomalies were an unresolved aside. There is no recorded follow-up within the same document, no appended analysis that attempts to reconcile the inconsistencies. It simply ends, leaving behind a set of measurements that describe empty spaces where none should be, and behaviours that hint at more than emptiness alone. And in the silence that follows those last recorded echoes, the question is no longer whether the voids exist, but what, if anything, has been moving within them. Operation High Jump, the official report versus the redacted pages. In the official records of Operation High Jump, the expedition appears as a carefully planned and uneventful mission carried out at the edge of the known world, though later declassified material would quietly suggest that something beneath the Antarctic ice had already drawn attention before the fleet ever arrived. Conducted in 1946 and 1947 under the direction of the United States Navy, the operation, formerly designated Task Force 68, mobilized one of the largest assemblies of naval and air power ever sent into polar conditions, including aircraft carriers such as the USS Philippine Sea, support vessels, and specialized reconnaissance aircraft designed to operate in extreme cold. On paper, its objectives were clear and practical: focused on training personnel, testing equipment in polar environments, and extending geographic knowledge of a continent still largely unmapped from the air. Yet when placed alongside earlier declassified seismic data that hinted at unnatural voids beneath the ice, the mission begins to feel less like routine preparation and more like a response to something already detected but not fully understood. According to the published summary, the operation was tasked with training personnel, testing equipment in polar conditions, and establishing a stronger American presence across Antarctica's coastal regions. The official report outlines the construction of temporary bases, the use of aerial photography to map previously unseen terrain, and the evaluation of cold weather survival techniques, all of which align with the geopolitical climate of the time as nations sought to extend their reach into remote and strategically ambiguous regions. Aircraft launched from carriers conducted reconnaissance flights over the ice, with some missions extending far inland beyond previously charted boundaries, relying heavily on navigational instruments in an environment where visual landmarks were often non-existent. These flights captured extensive photographic records that contributed to early mapping efforts, yet the raw scope of the interior ice sheet remained difficult to interpret with precision. Read in isolation, the report conveys a sense of methodical progress, with each objective addressed in measured detail and without indication of disruption. What survives in the declassified archives, however, is not a complete account, but a version of events marked by missing sections, redacted passages, and interruptions in the continuity of the record. Pages that should contain operational detail instead end abruptly, while certain sequences of activity appear compressed into summaries that replace what would normally be precise logs. In some instances, entire segments are removed, leaving only transitions between unrelated entries, as though the most critical moments were extracted rather than described. Notably, the most heavily altered sections are not the routine logistical reports or environmental summaries, but the technical records tied to navigation, aerial reconnaissance, and extended inland flights, areas that would normally provide the clearest picture of what the expedition actually observed. The absence feels concentrated rather than scattered, as though specific categories of information were selectively filtered out while leaving the surrounding context intact. Between different releases of the same documentation, subtle discrepancies begin to emerge, with certain technical descriptions shortened, altered, or removed entirely without explanation. Earlier versions reference environmental observations with a level of specificity that later editions seem to avoid, replacing descriptive language with broader terms that obscure rather than clarify. In a few cases, coordinates that once appeared in navigation logs are no longer present, creating gaps that make it difficult to reconstruct the full extent of the expedition's movements. Even Admiral Richard E. Byrd's publicly documented statements from the period, which emphasize the strategic importance of polar regions and future defense considerations, stand in quiet contrast to the tone of the internal records, which become increasingly restrained when describing the most remote inland operations. These variations suggest not a simple process of editing for clarity, but a deliberate refinement of what remains visible, shaping the narrative into something more controlled and less revealing. Within these fragmented reports, occasional references to unusual environmental conditions appear in language that remains deliberately vague, offering just enough detail to acknowledge deviation without defining its cause. Phrases describing irregular surface characteristics or unexpected atmospheric effects are recorded without elaboration, appearing briefly before the text returns to routine observations. While such terminology could be attributed to the unpredictable nature of Antarctic weather or terrain, its placement within already incomplete sections gives it a different weight, as though it marks moments where something was encountered but not fully documented. The inconsistency is not in the presence of these notes, but in their uneven distribution, appearing more frequently in sections tied to deeper inland traversal, where navigation was least reliable and reliance on instruments was greatest. When viewed alongside the earlier seismic anomalies, which suggested hollow spaces beneath the ice, these references begin to feel less isolated, hinting at a connection between what was detected from a distance and what may have been observed more directly. By the time the expedition drew to an unexpected close, the tone of the surviving records had shifted noticeably, replacing detailed observations with broader summaries that revealed far less than earlier entries. Operation High Jump had been planned to extend over a longer period, yet it concluded after only a few months, with official explanations emphasizing logistical challenges, extreme weather, and the inherent difficulty of sustaining operations in Antarctic conditions. While such factors were undeniably present, they had been anticipated from the outset, forming part of the mission's design rather than an unforeseen obstacle. The documentation offers no clear indication of a singular event that necessitated the early withdrawal, yet the reduction in detail near the mission's end suggests that something altered the nature of reporting itself, as though the priority shifted from recording what was found to limiting how much of it was preserved. Seen together, these omissions form a pattern that extends beyond simple classification, suggesting that the most significant observations may have been recorded elsewhere or removed entirely. The consistency of the gaps, their alignment with specific operational phases, and the transformation of detailed logs into generalized summaries all point toward a deliberate narrowing of the record. Even in the structure of what remains, there is a sense that certain threads were intentionally left unfinished, not because they lacked importance, but because their continuation would have revealed more than the archive was permitted to retain. Because whatever the expedition encountered was not erased, only carefully reduced to fragments that no longer explain themselves. Byrd's statement in declassified transcripts. Within archived interview transcripts attributed to Admiral Richard E. Byrd, the preserved words appear measured and deliberate, yet when placed alongside earlier declassified findings beneath the Antarctic ice, they begin to carry implications that extend beyond their original context. These records, drawn from interviews and recorded statements spanning the late 1940s and early 1950s, were never originally intended to be read as fragmented evidence, yet their later release into declassified archives has positioned them within a wider body of Antarctic documentation that already contains seismic anomalies and heavily redacted expedition logs. Read in isolation, the transcripts describe exploration, aviation, and the strategic importance of polar regions. But when viewed alongside other released materials, they begin to feel less like standalone commentary and more like carefully controlled pieces of a larger, incomplete narrative. In widely circulated public statements from the late 1940s, Byrd spoke of polar exploration in terms that emphasize strategy, aviation, and the expanding reach of human movement into remote regions. These remarks, preserved in official broadcasts and recorded interviews of the period, reflect a time when Antarctica was increasingly framed as both a scientific frontier and a space of geopolitical interest, where navigation, weather observation, and aerial reconnaissance were becoming essential tools of understanding. His language remained consistent with the broader tone of mid-century exploration discourse, where emphasis was placed on logistics, endurance, and technological capability rather than on speculation. Nothing within these public accounts directly suggests anything beyond conventional exploration, yet the precision and restraint of the phrasing establish a baseline against which later transcript variations become more noticeable. Across later declassified transcript fragments, however, subtle alterations in phrasing begin to emerge, revealing differences that are not immediately apparent but become difficult to ignore when examined closely. Sentences that once carried specific references to exploratory regions appear in altered form, with certain descriptive elements removed or replaced by broader, less defined language. In some instances, entire clauses are absent, leaving behind statements that still function grammatically but lack the detail present in earlier versions. These modifications do not fundamentally change the subject matter of the speech, yet they shift its clarity, producing a record that feels progressively less anchored in specificity the further it extends into remote or unexplored territories. Through comparison of these versions, certain expressions appear gradually softened, with precise language replaced by broader descriptions that reduce clarity without entirely removing meaning. Where earlier transcripts may reference particular operational areas or environmental conditions, later versions often substitute generalized phrasing that avoids direct characterization. This process does not eliminate information outright, but it disperses it, making it harder to identify where emphasis originally fell. The effect is subtle yet cumulative, creating a progression in which the speech remains intact at the surface level, while its underlying precision becomes increasingly diluted. Among the remaining statements, occasional references to unexplored or inaccessible regions persist, though they are framed in a way that avoids direct explanation of what made them significant. These passages maintain a careful neutrality, describing areas in terms of difficulty of access, environmental severity, or limited operational reach, without expanding into descriptive detail. In earlier, more complete versions of the transcripts, such references appear more specific, while in later fragments they are reduced to brief acknowledgements that carry little elaboration. The shift does not alter the existence of these references, but it changes their weight within the overall narrative, making them feel less like observations and more like controlled markers within a constrained account. At specific points within the transcript record, the continuity of speech itself seems to shift, as though segments of explanation were interrupted, condensed, or redirected into less detailed forms. The structure of certain passages suggests that conversational flow has been preserved in outline but not in full substance, with transitions between ideas occurring more abruptly than in surrounding sections. While such irregularities could reflect limitations in transcription or preservation, their occurrence across multiple documents introduces a pattern that is difficult to dismiss. The speech remains coherent, yet its internal pacing occasionally feels altered, as though the original cadence of explanation has been subtly adjusted in retrospect. When these patterns are considered alongside the earlier expedition records, the alignment between restricted language and geographically remote references becomes increasingly difficult to dismiss as a coincidence. In both cases, the most detailed descriptions tend to cluster around accessible or routine operations, while material associated with deeper inland activity or less familiar regions becomes progressively less precise. The parallel does not confirm intent, but it establishes a consistent relationship between proximity to the Antarctic interior and the reduction of descriptive clarity across different types of records, whether technical logs or spoken transcripts. What ultimately emerges from the collection of preserved statements is not a clear account, but a sequence of controlled expressions that seem to approach a subject without ever fully naming it. The transcripts remain formally complete in structure, yet their internal consistency weakens when traced across versions, suggesting that what is absent is not confined to missing pages or removed entries, but also embedded within the evolution of language itself. In this way, the record does not simply preserve what was said, but also reveals how what was said may have been carefully shaped after the fact. And with each carefully adjusted phrase, something unspoken becomes harder to separate from what was originally said. Soviet drilling logs recovered after decades. Recovered Soviet drilling archives, later released through fragmented declassification efforts, contain operational records from Antarctic ice core projects that were never originally intended for public analysis, yet now sit alongside other anomalous Antarctic findings that suggest deeper inconsistencies across multiple exploration programs. These documents originate from Soviet-era scientific drilling initiatives conducted during periods of intensified polar research, when deep ice core extraction became a key method for understanding long-term climate history and geological structure. While the records were designed as routine technical logs, their later recovery reveals a level of fragmentation that transforms them into something more uncertain than archival documentation alone would suggest, especially when viewed in parallel with other declassified Antarctic materials that already hint at irregular subsurface conditions. During documented phases of Soviet polar research, drilling operations were conducted with strict procedural consistency, focusing on extracting sequential ice cores to analyze atmospheric and geological conditions preserved over extended time periods. These programs relied on incremental drilling systems, where depth was carefully recorded at each stage, and environmental readings such as temperature, pressure, and structural resistance were logged at regular intervals. The intent was not exploration in the traditional sense, but controlled extraction of stratified ice layers that could preserve information spanning hundreds of thousands of years. Within this framework, the expectation was stability, predictable resistance from compacted ice, gradual changes in composition, and consistent mechanical feedback from drilling equipment as depth increased. Within the earliest sections of the recovered logs, drilling progression appears methodical and uninterrupted, with each recorded entry marking incremental increases in depth accompanied by stable environmental readings. The tone of the documentation reflects procedural discipline, with entries structured in a repetitive but precise format that emphasizes continuity over interpretation. Equipment performance is noted as stable, core samples are described in standardized terminology, and environmental conditions remain within expected operational parameters. At this stage of the record, nothing suggests deviation from anticipated geological behaviour, and the drilling process appears to follow established scientific expectations without interruption. As drilling operations advanced further into deeper ice strata, subtle variations began to appear in the technical records, reflected in brief adjustments to pressure readings and intermittent recalibration notes. These changes are recorded without commentary, appearing as routine technical corrections rather than anomalies requiring explanation. However, the frequency of recalibration entries begins to increase, particularly in sections where depth measurements approach ranges less frequently documented in earlier Antarctic drilling programs. The logs maintain their structured format, but the growing presence of corrective entries introduces a quiet disruption in the rhythm of the documentation, as if the system is compensating for conditions that are not fully aligning with expected mechanical behaviour. Between successive log entries, irregular gaps in documentation become increasingly apparent, with certain operational intervals recorded only in partial summaries or abbreviated status updates. These omissions are not explicitly acknowledged within the records themselves, but their presence becomes clear when comparing sequential entries that should, under normal procedural conditions, contain continuous data. Instead, some time segments are condensed into generalized statements indicating system stability or maintenance checks, without corresponding detailed measurements. The absence is subtle but persistent, suggesting either a breakdown in recording continuity or a deliberate reduction in log detail during specific phases of the operation. At depths approaching the most challenging recorded segments of the drilling program, the frequency of technical adjustments increases noticeably, accompanied by repeated system stabilization entries that suggest mounting operational strain. Equipment behavior is described in increasingly cautious terms, with references to mechanical resistance and variable drilling efficiency appearing more frequently in the logs. While deep ice drilling naturally introduces greater technical difficulty due to pressure and density changes, the consistency of these adjustments across multiple consecutive entries creates a pattern that stands out against earlier stable readings. The records continue to maintain their formal structure, but the underlying rhythm of the operation appears less uniform, as though the drilling process is encountering conditions that resist standard procedural interpretation. When the final available entries are examined in sequence, the progression of recorded data ends without transition or closure, leaving behind a continuous operational timeline that terminates mid-process. There is no concluding summary, no final equipment report, and no documented explanation for the cessation of entries. The last recorded measurements maintain the same structured format as earlier logs, yet they stop abruptly within an active phase of drilling activity, creating a discontinuity that is difficult to reconcile with standard archival completion practices. In technical documentation of this nature, operations are typically closed with summary entries, yet here the sequence simply stops, preserving the sense of an ongoing process that was never formally concluded. Among the later declassified fragments, only incomplete timestamps and partial log references remain, preserving the structure of the operation without retaining its concluding sequence. These fragments suggest that additional entries once existed but are no longer present in the recovered archive, leaving behind isolated pieces of a broader operational timeline. When reconstructed in order, they maintain the appearance of a controlled scientific program, yet the absence of final entries prevents any definitive understanding of how the drilling process ultimately resolved. The documentation exists in a state that is structurally complete in its progression but incomplete in its outcome, as though the record itself was interrupted at the moment closure was most necessary. What remains is not a conclusion of the operation, but a record that stops exactly where continuation should have begun. Lake Vostok Files, a sealed ecosystem documented. Beneath nearly 4 kilometers of Antarctic ice, Lake Vostok exists as one of the most isolated aquatic environments on Earth, its documented characteristics emerging from scientific reports that now align with earlier declassified findings suggesting unexplained conditions far below the surface. First identified through a combination of seismic sounding and radar surveys in the latter half of the 20th century, the lake revealed itself not through direct observation, but through the absence of expected resistance beneath the ice sheet, an anomaly that gradually resolved into the outline of a vast body of liquid water. When considered alongside earlier declassified records, that pointed to hollow spaces and irregular subsurface structures, the existence of a stable, hidden lake introduces a different kind of possibility, one defined not by emptiness but by containment. Encased under a continuous ice sheet for millions of years, the lake remains physically separated from the atmosphere, forming a closed system unlike any directly accessible environment. Estimates based on ice core analysis and glaciological modelling suggest that the overlying ice has remained largely undisturbed for extensive geological periods, effectively sealing the water below from external exchange. Unlike surface lakes, which interact constantly with atmospheric conditions, Lake Vostok exists under immense pressure, with temperatures hovering near the freezing point, but maintained in a liquid state due to the weight of the ice above. This combination of pressure, temperature, and isolation creates an environment where conventional assumptions about stability begin to shift, as the lake persists in conditions that appear static from above, yet remain dynamically sustained below. Attempts to reach such subglacial lakes have been approached with extreme caution, as drilling operations must avoid introducing external contaminants into ecosystems that have remained undisturbed over geological timescales. Scientific protocols developed for Antarctic drilling emphasize sterility and containment, recognizing that even minimal interference could alter a system that has evolved in isolation for millions of years. Efforts to access Lake Vostok have therefore proceeded slowly, with layers of procedural safeguards designed to prevent the introduction of foreign microorganisms or chemical agents. The very need for such precautions underscores the recognition that the lake is not merely a geological feature, but a potentially active environment whose internal conditions are both unknown and sensitive to disturbance. Indirect measurements derived from seismic, radar, and thermal data have provided estimates of the lake's temperature, pressure, and structural boundaries despite the absence of direct continuous observation. Radar imaging has traced the contours of the lake beneath the ice, revealing a body of water extending for hundreds of kilometers, while seismic reflections have helped define its depth and underlying bedrock. Thermal models suggest that geothermal heat from beneath the Earth's crust contributes to maintaining the lake in a liquid state, counteracting the freezing conditions imposed by the surrounding ice. These measurements, though indirect, present a consistent picture of a stable aquatic system existing under conditions that would seem inhospitable by surface standards, yet remain internally balanced over time. Within these inferred conditions, scientists have considered the possibility that microbial life could persist in complete isolation, supported by chemical energy sources rather than sunlight. Research into extremophiles, organisms capable of surviving in environments of high pressure, low temperature, and limited nutrient availability, has demonstrated that life can adapt to conditions once thought uninhabitable. In the case of Lake Vostok, the absence of sunlight eliminates photosynthesis as a primary energy source, suggesting that any potential life would rely on chemical interactions within the water or the surrounding rock. Supporting this possibility, studies of accretion ice layers formed when lake water freezes onto the underside of the overlying glacier have revealed trapped gases and microscopic inclusions that differ from the surrounding glacial ice, offering indirect glimpses into the lake's internal composition. While interpretations remain cautious due to the risk of contamination, these samples represent one of the few physical connections between the sealed lake and the external environment above it. Over extended periods of separation, closed ecosystems are known to develop internal stability, allowing biological processes to continue independently from external environmental influence. In such systems, nutrient cycles can become self-sustaining, driven by interactions between microorganisms and their environment in ways that do not require external input. Theoretical models of subglacial ecosystems suggest that, given sufficient time and stability, isolated bodies of water could support forms of life adapted specifically to those conditions, evolving along paths distinct from surface organisms. At the same time, the immense pressure exerted by the overlying ice may contribute to unusually high concentrations of dissolved gases, including oxygen, within the water, creating chemical conditions that differ significantly from typical deepwater environments. Combined with geothermal heat and potential mineral interactions at the lakebed, these factors suggest that the lake is not entirely static but part of a slow, ongoing internal system where circulation and chemical exchange may persist beneath the ice. Compared with other Antarctic subsurface findings, The characteristics associated with Lake Vostok suggest a contained system rather than the open or irregular structures indicated by earlier anomalies. Where seismic data hinted at hollow spaces and drilling records suggested interruption within the ice, the lake represents a defined boundary, an enclosed environment with measurable dimensions and inferred internal consistency. Yet this distinction does not resolve the broader pattern emerging across declassified Antarctic data. Instead, it introduces a parallel form of uncertainty, where the question shifts from the nature of space to the nature of what may exist within a sealed one. Limitations in direct sampling have left much of the lake's internal composition unresolved, with scientific conclusions relying heavily on indirect evidence and carefully controlled analysis. Even as technology has advanced, the challenges of accessing such an environment without contamination have slowed the pace of direct exploration, leaving key questions unanswered. The data that does exist offers a framework for understanding the lake's structure and potential, but it stops short of providing a complete picture. In this absence of direct observation, interpretation remains cautious, grounded in known scientific principles yet constrained by the limits of available evidence. And within an environment that has remained sealed for longer than recorded human history, the question is not simply what can survive there, but what has continued without ever being observed. Biological samples listed in restricted reports. Under controlled laboratory documentation associated with Antarctic research, a series of restricted reports references biological samples whose recorded characteristics do not fully align with the conditions from which they were reportedly obtained. These materials, preserved within limited circulation records and later partially declassified, do not present themselves as extraordinary findings, but rather as routine entries within broader analytical work, where samples are catalogued, examined, and assigned provisional classifications. Yet when viewed alongside earlier declassified data, subsurface anomalies, interrupted drilling logs, and sealed environments capable of sustaining isolated ecosystems. The presence of such samples begins to carry a different weight, suggesting that the question of what exists beneath the Antarctic ice may not be confined to theory or indirect measurement alone. Within standard scientific procedure, biological specimens are typically identified through established frameworks that compare structure, function, and environmental compatibility. Classification relies on observable characteristics, including cellular organization, metabolic pathways, and genetic markers, all of which are evaluated against known biological databases. Even in extreme environments, where life adapts to conditions once thought uninhabitable, organisms tend to exhibit recognizable patterns that allow them to be placed within existing taxonomic systems. This process does not require certainty at every stage, but it depends on the assumption that any newly observed form will at some level correspond to known biological principles. Among catalogued entries in these reports, certain samples are described in terms of cellular organization and morphology consistent with microbial life, yet lacking clear alignment with known classifications. Observations include references to structural formations that resemble known extremophiles, organisms adapted to survive under high pressure and low temperature, yet the descriptions stop short of assigning them to any specific group. In several instances, attempts were made to analyze genetic material extracted from these samples, using standard sequencing methods intended to compare DNA or RNA fragments against existing biological databases. While such analyses typically produce at least partial matches, the record suggests that some sequences proved difficult to align with known organisms, resulting in inconclusive or incomplete identifications that could not be confidently placed within established genetic frameworks. Against the environmental conditions documented in Antarctic subsurface regions, these descriptions introduce inconsistencies between expected biological limitations and observed structural features. The extreme cold, high pressure, and lack of sunlight would ordinarily restrict biological activity to highly specialized forms, yet some reported characteristics suggest metabolic resilience beyond what would typically be anticipated in such environments. Scientific studies of Antarctic ice cores and subglacial environments have previously identified microbial life adapted to survive under these constraints, often exhibiting slow metabolic rates and long periods of dormancy. However, the samples described in these reports appear to diverge from those expectations in subtle ways, as though their functional characteristics do not fully correspond to the survival strategies typically observed in known extremophiles. During repeated analytical attempts, classification results appear inconclusive, with provisional labels assigned and later reconsidered without definitive resolution. The reports document cycles of identification, reassessment, and revision, reflecting an ongoing effort to reconcile observed characteristics with established frameworks. In some cases, samples are tentatively associated with known categories, only for subsequent analysis to question those placements, leading to further uncertainty. This iterative process is not unusual in scientific research, yet the persistence of inconclusive results across multiple analyses introduces a pattern that suggests more than routine difficulty, indicating that the challenge lies not in insufficient data, but in the limitations of the classification system itself. Further complicating this process, expected biological indicators, such as consistent metabolic markers or predictable growth behavior, do not appear uniformly across observations, creating additional barriers to definitive classification. Although contamination remains a standard consideration in laboratory environments, the recorded handling procedures suggest that these samples were processed under controlled conditions designed to minimize external interference. Antarctic research protocols, particularly those involving subglacial or isolated environments, emphasize sterility and containment, recognizing that even minor contamination could compromise results. The reports reference adherence to these protocols, noting controlled extraction, transport, and analysis processes intended to preserve sample integrity. While the possibility of contamination cannot be entirely dismissed, its likelihood is reduced by the consistency of procedural safeguards described within the records, leaving open the question of whether the observed anomalies originate from the samples themselves. Across multiple entries, recurring characteristics begin to form a pattern, indicating that these observations are not isolated but appear in more than one documented instance. The repetition of similar structural descriptions, metabolic indicators, and unresolved classification outcomes suggests that the samples share underlying properties, even if those properties are not fully understood. In some cases, separate analyses conducted under comparable conditions appear to produce similar uncertainties, reinforcing the idea that these findings are reproducible rather than singular anomalies. This consistency strengthens the presence of the phenomenon within the records, transforming it from an isolated irregularity into a recurring feature of the data. Through restricted circulation and careful wording, the reports present their findings without direct interpretation, maintaining a tone that acknowledges uncertainty while avoiding definitive conclusions. The language remains technical and restrained, focusing on description rather than speculation, yet the absence of clear classification introduces an implicit tension within the documentation. The findings are recorded, preserved, and made available within limited contexts, but they are not resolved in the way that most biological analyses aim to achieve. Instead, they remain open, defined more by what cannot be concluded than by what can. Yet when a specimen resists every attempt to be placed within known boundaries, its presence raises a question that classification alone cannot resolve. Radar imaging data marked non-geological. From archived radar imaging surveys conducted across Antarctic ice sheets, a subset of declassified scan results classified as non-geological has drawn attention due to structural reflections that do not correspond to known natural formations beneath the surface. These imaging records originate from ground-penetrating radar systems used in polar research to map ice thickness and subglacial terrain, where radio wave reflections are typically interpreted through established geophysical models. In most cases, these surveys produce predictable layering signatures consistent with ice stratification, bedrock contours, or subglacial lake boundaries. However, within a limited portion of the archived datasets, certain reflected signals deviate from these expectations in ways that remain difficult to reconcile with standard geological interpretation, especially when considered alongside earlier findings from subglacial environments and anomalous subsurface records. As radio frequency signals are transmitted through layers of ice, their reflections typically reveal predictable variations in density, layering, and subglacial topography based on established geophysical principles. The method relies on the consistent behavior of wave propagation, where differences in material composition, produce measurable changes in signal return time and intensity. In Antarctic applications, this technique has been instrumental in identifying features such as buried mountain ranges, ice channels, and subglacial lakes, all of which produce irregular but interpretable reflection patterns. Signal behavior is also affected by depth-dependent attenuation, meaning that deeper structures normally produce weaker and less sharply defined returns due to scattering within the ice column. Against this expectation, the non-geological classifications appear counterintuitive, as they retain an unusual level of internal coherence despite being located in regions where signal degradation would typically obscure fine structural definition. In standard radar imaging interpretation, natural geological formations produce irregular but statistically consistent reflection patterns that correspond to rock density, ice stratification, or liquid water boundaries. These signatures vary in clarity depending on ice depth, signal strength, and environmental conditions, but they remain anchored in recognizable physical principles. Even complex formations, such as fractured bedrock or uneven subglacial sediment layers, produce reflections that can be mapped and categorized within existing geological frameworks. To reduce the risk of misinterpretation, radar datasets are typically subjected to cross-frequency validation, where multiple signal frequencies are compared to distinguish true subsurface structures from noise or instrument artifacts. In consistent geological features, reflection patterns remain stable across these variations, while false signals tend to degrade or shift unpredictably. Among selected imaging datasets, however, certain reflected signals display arrangements that deviate from expected geological behavior, producing patterns that appear unusually organized in their spatial distribution. These anomalies are not characterized by randomness or signal degradation, but by a level of structural regularity that stands apart from surrounding geological noise. The reflections appear with defined boundaries and repeated angular relationships that do not align with typical ice or rock formation signatures. Notably, in some cases, the boundaries of these reflected structures exhibit sharper transitions than expected at the recorded depths, where natural diffusion of signal energy would normally produce gradual gradients, rather than abrupt spatial edges. This inconsistency introduces additional difficulty in distinguishing whether the observed clarity originates from the subsurface feature itself or from an unrecognized interaction within the ice medium. When these anomalies are compared across multiple independent scans, similar structural configurations emerge, suggesting that the observed irregularities are not isolated to a single imaging pass or instrument reading. The repetition of these configurations across different survey locations and time periods indicates that the patterns persist under varying operational conditions, reducing the likelihood that they are the result of temporary technical artifacts. Cross-frequency comparison further reinforces this persistence, as the same structural outlines appear to maintain relative stability even when measured under different radar wavelengths, a behavior that typically corresponds to physically consistent subsurface formations rather than transient signal distortion. This consistency suggests an underlying source that remains stable across different measurement attempts, even when survey parameters are adjusted or recalibrated. During analytical reviews of these results, the reflected signals are described in terms of shape continuity and boundary definition, yet they resist classification within standard geological modelling frameworks. Attempts to model the structures using known subglacial formation processes produce incomplete or partial matches, where certain aspects of the reflections align with expected behavior while others remain unresolved. Standard artifact rejection protocols, including filtering for surface echo contamination and instrument backscatter, do not fully eliminate the presence of these patterns, further reducing the likelihood that they originate from known measurement errors. This persistence after multiple layers of validation introduces a persistent analytical gap, where the data appears structured but cannot be fully reconciled with established geological categories. In attempts to reconcile these patterns with known subglacial formations, proposed explanations fail to consistently account for the symmetry and repetition observed in the reflected structures. Hypotheses involving ice deformation, sediment displacement, or subglacial water flow account for some aspects of the data, but none provide a complete framework that explains the repeated structural coherence observed across multiple scans. The persistence of these unresolved features across independent analyses suggests that the limitation lies not in the quality of the data, but in the adequacy of the interpretive models being applied to it. Official classification records assign these imaging anomalies the designation non-geological, a term used to indicate that the observed formations do not align with recognized natural processes. This designation does not imply confirmation of artificial origin, but rather reflects the inability of current geological frameworks to categorize the observed structures within known formation mechanisms. In practice, the label functions as a procedural boundary, marking the point at which standard geological interpretation can no longer reliably describe the data without introducing unsupported assumptions or speculative extensions. And once a pattern is recorded clearly enough to be measured, it no longer remains dependent on interpretation to exist. Thermal signatures in satellite archives. Thermal detection systems operating over Antarctica register localized infrared deviations beneath ice formations that conventional cryospheric models classify as thermally uniform environments. These systems are designed to identify variations in emitted surface energy by measuring long-wave infrared radiation across extensive polar regions, where temperature conditions are expected to remain consistently stable and extremely low. However, the sensitivity of orbital thermal sensors is not absolute. Signal resolution decreases when attempting to infer subsurface conditions through thick ice, meaning that deeper thermal readings are reconstructed indirectly through modelled heat transfer rather than directly observed emission. Even with this limitation, the detected anomalies remain persistent across processed datasets, suggesting that the observed signals are not artifacts of measurement depth alone. Long-wave radiation measurement satellites rely on continuous calibration of emitted surface energy to map temperature variation across Earth's polar ice sheets. This process depends on highly sensitive sensors capable of distinguishing minimal differences in thermal emission, allowing researchers to construct detailed temperature profiles even in environments where variation is expected to be nearly non-existent. To ensure accuracy, raw data is routinely corrected for atmospheric interference, seasonal thermal drift, and sensor-based noise fluctuations that can distort low-temperature readings in polar regions. These filtering procedures are specifically designed to eliminate false positives caused by predictable environmental cycles, such as diurnal variation, orbital angle shifts, and seasonal radiation imbalance. Yet the anomalies in question remain detectable even after multiple stages of correction. Standard cryospheric theory treats Antarctic ice masses as thermodynamically stable systems in which internal heat variation remains statistically negligible over extended observation periods. The immense thickness of the ice sheet, combined with consistently low ambient temperatures, creates conditions in which heat transfer is slow and predictable, governed primarily by external atmospheric influence and minimal geothermal contribution from below. While geothermal heat does exist beneath Antarctica, it is typically expressed in localized and well-mapped zones with relatively low heat flux values that dissipate rapidly through overlying ice. The expectation within established models is that any subsurface thermal activity would produce weak, diffuse signals rather than concentrated, sustained anomalies. Certain thermal mapping outputs reveal isolated sub-ice regions where recorded energy levels exceed expected baseline thresholds for frozen environmental conditions. These anomalies do not present as random fluctuations but appear as concentrated zones of elevated heat signature embedded within otherwise stable thermal fields. The contrast between surrounding uniform cold and localized warmth creates measurable discontinuities in the data, prompting further analysis to determine whether these deviations originate from surface contamination, atmospheric distortion, or subsurface energy sources. In standard interpretation workflows, heat flux is treated separately from surface temperature readings, as it represents energy transfer from within the Earth rather than transient surface conditions, making persistent flux anomalies significantly more difficult to attribute to known environmental variability. Temporal correlation analysis of repeated measurements indicates that these thermal irregularities persist at fixed coordinates across multiple observational cycles. Rather than dissipating or shifting in response to changing seasonal conditions, the identified heat signatures remain stable in both position and intensity across extended time intervals. This persistence reduces the likelihood of transient atmospheric interference and suggests the presence of a stable underlying source. When seasonal correction models and orbital recalibration adjustments are applied, the anomalies remain unchanged, indicating that standard environmental normalization procedures do not account for their persistence. The repetition of identical thermal coordinates across independent data collections introduces a level of consistency that distinguishes these anomalies from typical short-term environmental variations. Subsurface depth modelling places the origin of detected heat signatures well beneath surface ice strata, extending into regions normally excluded from atmospheric or seasonal thermal influence. These projections are derived from inversion algorithms that translate surface temperature data into estimated subsurface energy distributions, allowing researchers to approximate the vertical position of heat sources without direct physical access. However, such models carry increasing uncertainty at greater depths, as signal attenuation through ice reduces precision and amplifies dependency on inferred thermal gradients rather than direct measurement. Even accounting for this uncertainty range, the magnitude of the detected heat flux exceeds what would typically be expected from background geothermal activity alone. Independent infrared sensing platforms operating under separate calibration protocols have produced matching thermal deviation patterns in identical geographic zones. The convergence of results across multiple satellite systems reduces the probability of instrument-specific error, as each platform employs distinct sensor architectures, processing algorithms, and calibration references. Cross-platform consistency is particularly significant in thermal imaging analysis, because independent systems are designed to diverge under uncertainty conditions. Yet, in this case, the anomalies remain spatially aligned across different datasets and processing methodologies. Despite this agreement, the origin of the heat signatures remains unresolved within current environmental models. Scientific interpretation frameworks currently classify these heat anomalies as unresolved, citing the absence of a compatible geothermal or environmental mechanism. This classification does not assign causation but rather reflects the limits of existing predictive models in accounting for sustained subsurface energy concentrations under thick ice coverage. In formal reporting structures, such unresolved classifications are reserved for cases where repeated validation fails to eliminate uncertainty through standard physical explanations, leaving the anomaly documented but analytically incomplete within established scientific understanding. When measured heat persists in a place defined by absolute cold, the anomaly stops behaving like data and starts behaving like a boundary in understanding itself. Acoustic logs recorded beneath research stations. Subglacial acoustic monitoring arrays installed beneath Antarctic research stations have recorded declassified vibration logs that contain structured frequency patterns originating from beneath thick ice formations. These monitoring systems are designed to capture minute mechanical disturbances transmitted through the ice column, where even low-energy events can travel long distances due to the crystalline structure of frozen layers. In typical operational conditions, such networks document sporadic and irregular seismic acoustic activity associated with ice movement, pressure release, or thermal fracturing. However, within select declassified records, certain acoustic sequences appear to deviate from expected natural variability, presenting organized patterns that persist across multiple recording intervals. What makes these particular signals notable is not only their repetition, but their confinement within a narrow and unusually stable frequency band, where most natural ice-generated noise would normally disperse across a wider spectral range. Ice-transmitted sound propagation behaves differently from air-based acoustics, as vibrational energy travels through crystalline structures with variable damping effects depending on density and internal fractures. In this medium, sound does not behave as a freely dispersing wave, but instead reflects, refracts, and attenuates in ways that are heavily dependent on ice composition and structural continuity. Because of this, acoustic interpretation beneath ice requires careful filtering of signal distortion caused by layered compression and microfracture scattering. Under normal analytical expectations, these distortions prevent the formation of stable rhythmic signatures unless a consistent physical source is repeatedly generating energy within the system. Yet in this case, the persistence of a confined frequency band suggests a level of signal stability that is statistically unusual for naturally generated cryospheric noise. Under normal polar conditions, background acoustic activity within ice sheets is dominated by low-amplitude cracking events caused by thermal stress and gradual glacial movement. These events typically produce short, irregular bursts of energy that decay rapidly and do not maintain structured timing patterns. The randomness of such signals is a defining characteristic used to distinguish natural ice behavior from engineered or repetitive mechanical sources. Even large-scale glacial shifts tend to generate broadband noise profiles rather than narrowly defined rhythmic intervals, reinforcing the expectation that persistent acoustic structure beneath ice is highly unusual. In validated monitoring systems, stations are also engineered to remain acoustically isolated from one another, ensuring that cross-site interference or signal duplication cannot occur through shared instrumentation pathways. Certain sections of recorded acoustic data reveal repeating vibration intervals that maintain consistent timing patterns rather than the irregular dispersal expected from natural ice fracturing. These sequences appear as structured pulses embedded within otherwise low-level background noise, with spacing that remains unusually stable across extended recording periods. The persistence of this timing consistency is notable because natural cryospheric processes rarely generate periodic acoustic emissions without external forcing mechanisms. In several instances, the rhythm of these vibrations does not degrade over time, suggesting a sustained source rather than a dissipating mechanical event. Additionally, signal arrival analysis indicates that timing offsets between geographically separated stations remain unexpectedly synchronized, despite the physical expectation that vibrations traveling through heterogeneous ice would produce measurable delay variations. Extended monitoring sequences show that these rhythmic acoustic signatures persist across multiple recording cycles without significant variation in frequency or amplitude decay. This stability persists even when environmental variables such as temperature fluctuation, surface pressure changes, and seasonal ice stress are accounted for in post-processing adjustments. Normally, such variables introduce measurable drift in acoustic signatures, causing gradual distortion or signal attenuation. The absence of these expected deviations suggests that the recorded pattern is not merely a transient product of environmental instability, but a persistent feature within the acoustic data set. When filtered through standard attenuation models, the signal should weaken progressively with distance. Yet, in these cases, detectable intensity remains unexpectedly consistent across separated observation points. Comparative analysis between station-based sensor networks indicates that identical vibration patterns appear simultaneously across geographically separated monitoring points beneath the ice sheet. These stations operate independently, utilizing separate calibration systems and data processing pipelines, which reduces the likelihood of synchronized instrumental error. The replication of identical acoustic sequences across multiple points of detection implies a coherent propagation of vibrational energy through the ice medium. In addition, the uniformity of arrival timing across stations contradicts expected propagation delay models, which would normally introduce slight but measurable offsets based on distance and ice density variation. The absence of such offsets further complicates standard geophysical explanations that rely on predictable wave dispersion behavior. Interpretative modeling attempts to correlate the detected acoustic sequences with known geophysical processes, but they fail to produce consistent matches with any recognized subglacial activity. Hypotheses involving ice shelf movement, basal sliding, or fluid flow within subglacial lakes account for certain aspects of the acoustic signature, but fail to reproduce the strict periodicity and cross-station synchronization observed in the data. Even when models are adjusted to account for complex layered propagation effects, the rhythmic stability of the signal remains outside expected behavioral ranges for naturally occurring cryospheric processes. Official evaluation reports describe the recorded acoustic signatures as unresolved vibrational anomalies, noting the absence of any confirmed mechanical or environmental source. This classification reflects a procedural boundary in which recorded data cannot be reliably attributed to known physical mechanisms under current analytical frameworks. In such cases, the anomalies are retained within monitoring systems for continued observation, but without assignment of causal explanation, as doing so would require assumptions beyond verified physical evidence. Vibrations recorded through the ice remain traceable in the data, yet no identifiable source of motion exists beneath the station network. The Antarctic Treaty's lesser-known restrictions. Antarctic Treaty governance documentation outlines a multinational legal framework established to regulate territorial claims, scientific cooperation, and demilitarization across the Antarctic continent. Yet certain declassified references suggest the presence of additional restrictions not fully explained within public treaty summaries. These documents describe a system designed to maintain Antarctica as a zone dedicated to peaceful scientific activity, where military operations are prohibited and collaborative research is encouraged under internationally agreed conditions. The framework itself is widely recognized as one of the most stable examples of multilateral environmental governance, with participating nations agreeing to suspend territorial sovereignty claims while allowing shared scientific access under strict regulatory oversight. However, within layered administrative records, certain procedural notes indicate the existence of constraints that extend beyond these commonly cited principles. International treaty provisions governing Antarctic activity define standardized principles centered on peaceful research use, environmental preservation, and the suspension of sovereign territorial enforcement among participating nations. These foundational rules are implemented through a structured system of inspection rights, allowing designated representatives from treaty signatory states to visit research stations and verify compliance with agreed obligations, sometimes with limited advance notice under specific procedural conditions. In parallel, stations operating under the treaty are required to submit detailed operational logs, environmental impact assessments, and logistical reports to ensure transparency in scientific activity. These reporting mechanisms are designed to maintain accountability across all active installations, ensuring that no single research entity operates outside shared oversight frameworks. Regulatory classifications applied to Antarctic operations typically include environmental protection zones, scientific permitting structures, and logistical oversight mechanisms designed to ensure controlled access to sensitive regions. These classifications are generally based on ecological fragility, scientific value, or logistical difficulty, with access permissions adjusted accordingly to minimize environmental disruption. In addition to fieldwork approvals, participating nations are obligated to exchange research findings and observational data through standardized reporting channels, reinforcing a system of collective scientific visibility. Antarctic treaty consultative meetings further reinforce this structure, providing an annual forum where policy adjustments are made through consensus rather than unilateral decision, ensuring that governance remains distributed across all member states. Some sections of administrative records reference supplementary access limitations that do not align directly with standard ecological conservation frameworks or conventional research safety protocols. These references appear in procedural annotations and internal compliance documents rather than in public treaty summaries, suggesting the presence of additional interpretive layers within the governance structure. While most restrictions can be traced to identifiable environmental or operational concerns, these supplementary limitations are described in broader terms that emphasize control, coordination, and oversight, without providing detailed justification tied to ecological or scientific necessity. In certain cases, emergency environmental protection clauses allow rapid restriction of specific zones, but such measures are typically expected to include documented justification linked to observable environmental risk factors, making the absence of explicit reasoning in select entries particularly notable within the administrative record. Hierarchical authorization systems embedded within Antarctic governance structures require multi-tier approval processes involving national agencies, scientific committees, and intergovernmental review bodies before certain zones may be accessed. These systems are designed to ensure that no single entity can independently authorize activities in sensitive regions without collective oversight. Requests for access are evaluated through sequential review stages, where logistical feasibility, environmental impact, and scientific merit are assessed before final approval is granted. Inspection protocols embedded within the treaty framework further reinforce this oversight structure, allowing independent verification of station activity to ensure compliance with established international obligations. Together, these mechanisms create a governance environment in which access is not only controlled, but continuously subject to verification and cross-checking among participating parties. Comparative analysis of treaty implementation records indicates that specific geographic coordinates are subject to more restrictive entry conditions than adjacent regions with similar environmental classifications. These discrepancies are not always directly explained by observable differences in terrain, biodiversity, or climatic vulnerability, which are typically the primary factors guiding access restrictions. Instead, certain coordinates appear to fall under elevated administrative control categories, where procedural barriers remain in place even when conventional environmental justification is not explicitly stated. The coexistence of clearly defined environmental protection zones alongside these less explicitly justified restrictions introduces an asymmetry in how access governance is applied across the continent, particularly when evaluated against the otherwise standardized classification system. Interpretive reviews of regulatory language reveal instances where procedural restrictions are defined without explicit operational justification beyond generalized reference to compliance and oversight requirements. In such cases, documentation emphasizes adherence to protocol without detailing the underlying rationale for specific limitations. While international agreements often employ broad language to accommodate evolving operational contexts, Antarctic governance records exhibit repeated instances where geographic specificity is paired with non-specific justification language. This combination creates analytical difficulty when attempting to align procedural restrictions with clearly defined environmental or logistical criteria. Official treaty summaries emphasize transparency and scientific openness, yet certain archived policy annotations acknowledge the existence of controlled access provisions that are not elaborated in publicly distributed documentation. These annotations are typically framed as administrative safeguards, intended to preserve operational integrity and ensure coordination among participating nations. Despite the system-wide emphasis on shared scientific access and data exchange, the presence of selectively detailed restrictions suggests a layered governance structure in which not all procedural boundaries are fully disclosed at the same level of specificity. This does not contradict the treaty's formal objectives, but it does highlight a structural difference between general principles and localized administrative application. Some restrictions define the boundaries of access clearly, while others exist in a form where the boundary is visible but the reason for its placement is not. Maps with deliberate omissions. Cartographic survey fragments recovered from Antarctic mapping archives show not continuous documentation, but segmented representations in which entire geographic sections are absent between successive recorded iterations. These fragments originate from compiled survey datasets that combine historical expedition, mapping, satellite-derived reconstructions, and later geospatial standardizations, yet the continuity normally expected in sequential cartographic records is interrupted in specific Antarctic sectors. Instead of a stable progression of map detail, the archival sequence reveals gaps where terrain representation appears to have been deliberately excluded from intermediate versions while remaining present in earlier and later editions. The resulting pattern does not resemble typical data loss, but rather selective discontinuity embedded within otherwise intact mapping documentation. Satellite-derived mapping composites integrated with aerial survey overlays reveal that Antarctic terrain representation is constructed through layered reconstructions rather than single-source cartographic capture. Modern mapping of polar regions typically depends on the fusion of multiple observational systems, including orbital imaging, airborne radar scanning, and ground-verified geodetic correction points. These systems are designed to reinforce one another, producing high-confidence terrain models that reduce ambiguity in spatial interpretation. Antarctic datasets are commonly processed through standardized projection systems, such as polar stereographic models, which are intended to minimize distortion at extreme latitudes. However, even small projection adjustments at the pole can produce amplified boundary shifts when layers are combined across different time periods. Despite these safeguards, certain composite outputs still exhibit localized misalignment where overlapping datasets fail to converge precisely. Geodetic reference systems normally preserve spatial consistency across global mapping grids, yet Antarctic coordinate records display localized discontinuities where fixed reference points fail to align across datasets. These systems depend on standardized datum frameworks such as global reference models that ensure coordinates remain stable across independent surveys. Even minor datum shifts typically produce predictable, measurable offsets that can be corrected through recalibration procedures. In the Antarctic records under review, however, coordinate inconsistencies recur in the same geographic zones across multiple datasets, suggesting that the deviations are not random measurement drift but repeated anomalies tied to specific spatial regions. Comparisons between early expedition-era cartographic outputs and modern geospatial reconstructions expose abrupt spatial discontinuities that do not correspond to known projection corrections or measurement recalibrations. Historical Antarctic mapping relied heavily on exploratory surveys, aerial photography, and manual charting, often refined later by satellite confirmation. Normally, discrepancies between early and modern maps are resolved through correction layers that account for improved resolution and measurement accuracy. While resolution limits in early datasets can explain minor boundary imprecision, they cannot account for entire regions disappearing and reappearing between successive map generations without traceable transitional layers or explanatory revision notes. Historical sequencing of Antarctic mapping revisions reveals that certain terrain boundaries do not evolve gradually, but instead reappear in altered forms after periods of complete omission from intermediate records. Modern cartographic systems typically rely on version-controlled datasets, where every modification is stored in sequential layers that allow full reconstruction of prior states. Under such systems, no geographic feature is expected to vanish without leaving a recoverable digital trace in earlier iterations. Yet in select Antarctic sequences, intermediate versions are missing entirely for specific regions, breaking continuity in a way that prevents full reconstruction of how spatial changes occurred over time. Independent cartographic datasets produced by separate national agencies exhibit conflicting spatial interpretations of identical Antarctic regions, despite reliance on shared satellite and geodetic observation systems. These agencies operate under standardized geospatial conventions intended to ensure interoperability between mapping outputs, meaning that core terrain features should remain consistent regardless of origin. The presence of repeated discrepancies in the same regions across independent systems suggests that the divergence is not caused by sensor error or projection incompatibility alone, but by inconsistencies that persist even when datasets are normalized to identical reference frameworks. Geospatial correction logs typically contain explanatory metadata for alterations in mapped terrain, yet specific Antarctic regional adjustments appear without corresponding revision justifications in archival documentation. In standard geospatial practice, every modification is expected to include metadata detailing the reason for change, whether due to improved resolution, updated satellite imagery, or recalibrated reference systems. The absence of such documentation in specific Antarctic cases leaves spatial alterations recorded only as final outputs, without accessible intermediate reasoning or technical explanation that would normally ensure traceability across dataset revisions. Official cartographic standards emphasize reproducibility and traceable revision history, yet Antarctic mapping records contain instances where spatial deletions persist without recoverable editorial lineage. This deviates from expected geospatial version control systems, where layered data structures preserve each stage of modification for auditability and reconstruction. Even when historical datasets remain intact in other regions, Antarctic-specific entries occasionally lack intermediate versions entirely, creating breaks in the continuity of spatial documentation that cannot be resolved through standard archival comparison methods. Certain Antarctic mapping records preserve coordinates that appear consistently across editions, yet the terrain associated with them is no longer rendered in any accessible cartographic layer. Scientist testimonies buried in archives. Field reports written by Antarctic research personnel include documented observations that appear in early records but are absent from later published accounts, despite being attributed to the same expedition work. These records form part of declassified documentation that has drawn attention not for what they openly describe, but for what they no longer contain in their finalized forms. In several instances, preliminary notes reference encounters or environmental conditions that were initially recorded in neutral technical language, only to be omitted or condensed in ways that remove specific descriptive elements. Within the same body of declassified material that has contributed to the broader pattern of anomalies beneath Antarctica, these missing statements appear not as isolated editorial decisions, but as part of a recurring pattern where recorded observation does not consistently survive the transition into public scientific discourse. Research teams operating in polar environments follow structured documentation procedures in which raw observations are recorded, reviewed, and gradually refined before entering formal publication channels. Field notes are typically compiled during expeditions under controlled formats, capturing environmental data, instrumentation readings, and any unexpected occurrences encountered during operations. These initial records are then incorporated into draft reports, where language may be clarified or standardized without altering the underlying observations. Before any material reaches external publication, it often passes through internal review layers that include institutional oversight, senior researcher evaluation, and compliance checks designed to ensure that findings meet established scientific and organizational standards. This multi-stage process creates several points at which content can be evaluated, modified, or withheld before formal dissemination. Peer-reviewed scientific work relies on the expectation that original field notes and final publications maintain continuity in their recorded findings, allowing independent verification through traceable documentation. This continuity is essential not only for replication of results, but also for the integrity of the scientific process itself, where each stage of documentation supports the next. Within internal workflows, however, field observations are sometimes categorized based on their level of verification, ranging from confirmed data to preliminary or anomalous entries that require further validation. While such classifications are standard practice, they can influence whether certain observations are carried forward into formal reports or retained as unverified internal notes. Deviations from expected continuity are typically accompanied by clear editorial or methodological explanations, yet in these cases, such explanations are not consistently present. Initial observation entries from certain Antarctic expeditions contain statements that do not carry forward into the finalized reports associated with the same research outcomes. These statements often appear embedded within otherwise routine field descriptions, lacking overt emphasis or speculative interpretation, yet they are later absent from the structured summaries presented in official publications. The removal of such content does not appear to follow a consistent thematic pattern that would suggest simple irrelevance or redundancy, but instead affects specific descriptive passages that remain identifiable in earlier drafts. This selective omission introduces a discontinuity between recorded observation and reported findings that is not easily explained through conventional editorial processes. Follow-up interviews and correspondence show instances where researchers decline to elaborate on previously recorded observations when later asked to clarify or expand upon their findings. In documented exchanges, responses shift from initial descriptive detail to more generalized statements that avoid direct engagement with earlier recorded content. While such restraint can reflect standard scientific caution, particularly when observations cannot be independently verified or replicated, the repeated occurrence of this pattern across separate cases introduces a consistent reduction in specificity after initial documentation. The transition from recorded detail to later ambiguity becomes a defining feature within these accounts, suggesting a narrowing of what is considered appropriate for continued discussion. Draft versions of scientific manuscripts reveal passages describing field conditions that are not present in the officially published versions released through academic channels. These drafts often include detailed observational language that is later reduced or removed entirely during the revision process, without accompanying notes indicating the rationale for such changes. In standard publication workflows, substantial alterations are typically documented through revision tracking or editorial commentary, particularly when they involve the removal of descriptive content. The absence of such documentation in these cases leaves only the difference between versions as evidence that content once present has been intentionally excluded. Editorial revision trails in some Antarctic research records do not provide a clear pathway explaining how specific observational content was removed between early drafts and final publications. Version histories that would normally allow reconstruction of editorial decisions appear incomplete or lack the expected level of detail for certain entries. At the same time, institutional data retention practices often preserve full datasets and documentation internally, even when only a portion of that material is selected for publication. This creates a divergence between what is stored and what is shared, where the existence of more complete records does not guarantee their inclusion in publicly accessible outputs. Without a continuous revision trail, the process by which observation becomes a mission cannot be fully reconstructed from available documentation. Internal documentation retained by research institutions contains variations of expedition records that differ from publicly accessible reports, with certain details appearing only in restricted versions. These internal records often preserve a level of descriptive specificity that is not reflected in published materials, suggesting that multiple versions of the same observational data may exist simultaneously within different layers of institutional record keeping. The coexistence of these parallel versions introduces a structural separation between what is documented and what is disseminated, leaving certain observations confined to records that are not part of standard scientific circulation. Recorded statements persist in earlier documentation, even as later versions present the same events without any indication that those statements were ever made. Magnetic data logs flagged as unresolved. Magnetic variations observed beneath Antarctic ice have been documented in declassified entries marked unresolved, where repeated measurements fail to produce a stable interpretation. These entries appear alongside broader records that have contributed to the growing pattern of anomalies associated with the continent's subsurface, yet they differ crucially. The data does not simply indicate something unusual, but resists remaining consistent long enough to be defined. In contrast to other forms of detection that produce identifiable signals, these magnetic readings fluctuate within the bounds of precision instruments while refusing to align with any known model of subsurface behavior. The result is not the absence of data, but the presence of measurements that remain intact and repeatable in form, yet unstable in meaning. Magnetometers operating in polar conditions detect subtle distortions in Earth's magnetic field, translating underground influences into measurable fluctuations. These instruments are calibrated to extreme sensitivity, capable of identifying variations caused by differences in rock composition, mineral deposits, or changes in subsurface density. In Antarctica, such tools are frequently used to map hidden geological structures beneath thick ice sheets, where direct observation is not possible. Their reliability depends on the assumption that magnetic responses correspond to physical conditions that can be consistently measured, allowing researchers to reconstruct what lies beneath based on repeatable signal patterns. Earth's geomagnetic field typically behaves in consistent patterns shaped by core dynamics and crustal composition, allowing predictable mapping of subsurface structures. While natural variations do occur due to solar activity or localized geological features, these changes follow identifiable trends that can be filtered, modeled, and accounted for during analysis. In most environments, magnetic surveys produce stable datasets that converge toward a single interpretation, even when initial readings contain minor inconsistencies. This stability is also expected across time, meaning that repeated measurements taken days or weeks apart in the same location should remain closely aligned unless a significant physical change has occurred in the subsurface environment. Unexpected fluctuations begin to emerge in specific Antarctic regions where magnetic intensity shifts without correlating to known geological formations. These variations do not align with established magnetic signatures associated with rock types or mineral concentrations typically found beneath the ice. Instead, the readings move between values that suggest incompatible conditions, as though the subsurface environment is presenting conflicting magnetic characteristics within the same location. Even after standard environmental noise sources are considered, including solar activity and atmospheric interference, the anomalies persist in forms that do not match expected external or internal magnetic influences. Repeated passes over identical coordinates generate readings that vary in strength and direction, preventing the formation of any consistent signal pattern. In controlled survey operations, flight paths and measurement intervals are carefully standardized to ensure that repeated observations can be directly compared. Under normal circumstances, these repeated passes refine the dataset, reducing uncertainty and reinforcing the reliability of the results. Modern processing systems also apply noise filtering algorithms designed to remove distortions caused by solar storms, ionospheric disturbances, and equipment drift. Yet in these Antarctic datasets, the anomalies remain visible even after such filtering has been applied. Multiple instruments positioned within the same operational parameters produce contradictory outputs, with some detecting variation while others register none. These instruments are typically calibrated against shared reference standards before deployment, ensuring that differences in readings can be attributed to environmental factors rather than equipment inconsistencies. When discrepancies do occur, they're usually traceable to identifiable calibration errors or localized interference. In this case, recalibration cycles and cross-check verification procedures fail to resolve the divergence, as instruments continue to disagree even when tested against known magnetic reference zones used to standardize field accuracy. Unresolved classifications are assigned when observed values cannot be aligned with established magnetic or geological models used in standard interpretation frameworks. This designation does not imply the absence of data or a failure of instrumentation, but rather the inability to reconcile the measurements with known physical explanations. In technical terms, the readings remain valid, yet they cannot be placed within any existing category that would allow them to be understood or predicted. In addition, standard interpretation protocols distinguish between crustal magnetic sources and external field disturbances caused by space weather or atmospheric interactions, yet these Antarctic readings do not consistently match either category, remaining unclassified even after multiple analytical attempts. Attempts to simulate these variations through conventional geomagnetic equations fail to reproduce the observed behavior under controlled analytical conditions. Computational models that account for known influences, including crustal anomalies, external magnetic disturbances, and instrumental sensitivity, do not generate outputs that match the recorded fluctuations. Even when parameters are adjusted beyond typical ranges, the resulting simulations fail to replicate the instability observed in the field. This gap between measurement and model leaves the data suspended without a framework capable of explaining it. The measurements persist with precision, yet the conditions required to produce them remain undefined. Subglacial tunnel networks in geological reports. Glaciological reconstruction studies of Antarctica's ice sheet structure include declassified analyses referencing interconnected subglacial void formations identified through multi-method terrain modelling. These references appear within technical assessments of icebed interface mapping, where multiple survey techniques converge on subsurface irregularities that cannot be explained through isolated geological processes alone. Rather than describing singular cavities or localized depressions, the compiled analyses indicate recurring spatial relationships between voids detected across separate regions of the continent. Within the broader context of Antarctic subsurface investigation, these formations are documented not as anomalies in isolation, but as part of a recurring structural pattern embedded beneath the ice sheet. Ice-penetrating radar systems used in polar research transmit electromagnetic pulses through ice layers, capturing reflected signals that reveal variations in density and subsurface structural discontinuities. These systems are designed to differentiate between ice strata, bedrock boundaries, and liquid water interfaces by analyzing signal return strength and timing delays. In standard conditions, radar cross-sections produce layered representations of ice accumulation over time, allowing researchers to reconstruct climatic and geological history. The resolution of these systems is strongest in localized scans, but becomes increasingly complex over extended ranges, where signal interpretation depends on stitching together multiple survey passes into coherent subsurface models. When anomalies occur, they are typically expressed as irregular reflectors or disrupted layering, but remain interpretable within established glaciological frameworks. Under typical glacial conditions, subsurface voids appear as isolated formations shaped by pressure, melting processes, or bedrock irregularities without long-range spatial continuity. These features are generally limited in scale and distribution, forming localized pockets or channels that correspond to known physical mechanisms such as basal melting, geothermal heating, or structural deformation of ice under pressure. The expectation within glaciological modelling is that such voids remain independent and discontinuous unless influenced by identifiable environmental forces capable of linking them through physical processes. Even more importantly, Antarctic ice sheets are not static systems, they're in continuous motion, slowly deforming and shifting under their own mass, meaning any stable subsurface configuration would typically be distorted or gradually reconfigured over time. unexpected spatial alignment emerges in certain Antarctic datasets, where separate cavities appear positioned in consistent directional sequences across extensive ice-covered regions. These alignments do not conform to random distribution patterns expected from independent formation events, instead suggesting a level of spatial ordering that persists across wide geographic separation. The repetition of directional consistency introduces a structural quality to what would normally be interpreted as unrelated voids, creating the impression of continuity where none is typically expected in glacial environments. At this stage of interpretation, it becomes important to note that individual survey missions often cover only segmented portions of the continent, meaning that large-scale patterns are reconstructed by merging partial datasets collected across different expeditions and timeframes. Sequential mapping outputs suggest that multiple subglacial voids maintain geometric relationships that extend beyond localized formation processes, forming extended linear and branching configurations. When visualized through integrated subsurface models, these voids appear to connect across distances that exceed the expected range of individual geological influence zones. This configuration is not limited to a single region, but appears across multiple survey zones, where separate datasets produce compatible structural alignments despite being collected under different conditions and timeframes. The persistence of these alignments across independently gathered survey segments adds further weight to the interpretation that the observed pattern is not an artifact of a single measurement campaign, but a repeated feature emerging from multiple observational layers. Comparative analysis between radar cross-sections, gravity anomaly readings, and seismic reflection profiles shows convergence toward identical subsurface void patterns despite differing measurement methodologies. Each method operates on distinct physical principles: electromagnetic reflection, gravitational variation, and acoustic wave propagation, yet all indicate similar spatial distributions of subsurface emptiness. In standard geological interpretation, such convergence strengthens confidence in structural modelling, as independent techniques reinforcing the same result typically reduce uncertainty and increase interpretive reliability. Established glaciological models fail to replicate the observed arrangement of connected cavities when applying known mechanisms such as basal melting, ice deformation, or geothermal activity. Simulated reconstructions based on these processes produce fragmented or irregular void distributions, lacking the directional continuity and spatial coherence present in the recorded datasets, even when variables are adjusted to account for extreme environmental conditions. The resulting models do not reproduce the extended connectivity suggested by the observational data. This discrepancy indicates a limitation in current explanatory frameworks rather than a failure of measurement resolution. Spatial reconstruction of the icebed interface indicates that void distribution follows a structured configuration that remains consistent across independently collected datasets and survey timelines. This consistency persists even when data is gathered using different equipment platforms or under varying environmental conditions, suggesting that the observed pattern is not dependent on a single methodological approach. The persistence of structural alignment across datasets implies a stable underlying geometry that is repeatedly detected regardless of the analytical perspective used to examine it. The combined measurements do not resolve into isolated features, but instead outline a continuous subsurface configuration extending beneath the ice sheet without interruption. The classified incident report from an Antarctic station. The document surfaced quietly, filed among routine logistical reports and weather summaries, its title stripped down to a numerical designation that revealed nothing of its contents. Yet within its pages lay one of the few declassified records that appeared to suggest something was moving beneath the Antarctic ice. It originated from a research station operating along the eastern edge of the continent, in a region where the ice sheet stretches for thousands of kilometers and conceals subglacial lakes sealed off for millions of years. Antarctica itself, governed under the Antarctic Treaty System since 1961, has long been a place where scientific transparency is encouraged in principle. Yet certain operational reports, particularly those involving emergencies, have historically passed through layers of review before release. What remained in this case was not a complete narrative, but an emergency log compiled in real time, its entries fragmented, abrupt, and marked by a shift in tone that began with routine observation and ended in something far more urgent. The station referenced in the file was situated on a stable section of ice above one of Antarctica's known subglacial systems, part of a network of more than 400 lakes identified through decades of radar surveys. Among these, Lake Vostok stands as the most well-known, buried beneath nearly 4 kilometers of ice and isolated for an estimated 15 million years, a fact that has long fueled both scientific curiosity and quiet speculation. While the report did not explicitly name the lake beneath the station, it referenced drilling operations consistent with known efforts to access such environments without contaminating them, a process that requires sterile equipment and meticulous control of pressure and temperature. For years, researchers have approached these hidden waters cautiously, aware that they may contain microbial life adapted to extreme conditions, yet the tone of this report suggested that what was encountered did not align with those expectations. Initial entries in the log followed a familiar rhythm, documenting drilling depth, ice composition, and equipment performance with the precision expected of polar research teams. The ice core data indicated gradual transitions through compacted snow layers into dense glacial ice, consistent with known stratification patterns across East Antarctica, where snowfall accumulates slowly and preserves atmospheric history within trapped air bubbles. At a recorded depth approaching the lower threshold of the ice sheet, instruments began registering minor fluctuations, subtle variations in temperature and pressure that, while unusual, were not immediately considered alarming. Similar anomalies have been observed in other deep drilling projects, often attributed to shifts in ice density or the presence of brine pockets trapped beneath the surface, and for a time, the team appears to have treated the readings as part of that known spectrum. The first indication that something had changed appeared not in the numerical data, but in the language of the log itself, where precise measurements gave way to brief, incomplete notes. A reference to unexpected resistance appeared alongside a sudden halt in drilling progress, followed by an entry noting a recalibration of equipment that yielded no clear explanation. In Antarctic drilling operations, resistance at depth can signal contact with bedrock or sediment layers, yet the instruments reportedly detected neither, instead registering a density profile that did not match known geological formations. The report described the obstruction as neither solid nor fluid in the conventional sense, an observation that, while vague, marked a departure from standard classifications used in glaciology and subglacial research. Moments later, the log recorded a sharp deviation in pressure readings within the borehole, accompanied by a localized temperature increase that could not be accounted for by mechanical friction alone. Antarctica's interior is among the coldest places on Earth, with temperatures at stations like Vostok Station having dropped to 2 degrees Celsius, making any sudden thermal variation at depth both rare and significant. The instruments, calibrated to detect minute environmental changes, registered a rise that suggested an active source rather than a passive anomaly, prompting an immediate suspension of drilling activities. It was at this point that the tone of the report shifted decisively, with entries becoming shorter, more urgent, and increasingly focused on containment rather than exploration. The emergency log then noted the detection of vibrations emanating from below the drill site, initially faint but rapidly increasing in intensity. Seismic activity in Antarctica is not unheard of. The continent experiences occasional ice quakes and minor tectonic movements, particularly along the edges of the East Antarctic ice sheet. However, the pattern described in the report did not correspond to typical seismic signatures, instead appearing rhythmic, almost patterned, as though originating from a source capable of sustained motion. The station's monitoring equipment, designed to distinguish between natural and mechanical disturbances, failed to classify the signal, leading to a series of entries that questioned the reliability of the instruments themselves. As the vibrations intensified, communication logs within the report indicated growing concern among the research team, with references to structural stress on the drilling apparatus and surrounding ice. The borehole, which had been carefully maintained to prevent collapse, began to exhibit irregular deformation, suggesting external pressure being applied from below rather than above. Such a phenomenon runs counter to the expected behavior of ice under stress, where pressure typically increases with depth due to the weight of overlying layers, not from an upward force. The report described the deformation as gradual at first, then accelerating, forcing the team to initiate emergency protocols designed for rapid shutdown and evacuation. What followed was documented in a series of time-stamped entries that conveyed urgency without explanation, noting the sealing of the borehole, the shutdown of non-essential systems, and the preparation of transport vehicles for immediate departure. Antarctic stations operate under strict safety procedures, given the continent's isolation and extreme conditions, yet full evacuations are exceedingly rare and typically reserved for catastrophic events such as fire or structural failure. The absence of such triggers in the report, no mention of external weather threats or internal system breakdowns, left the cause of the evacuation tied solely to the subsurface anomaly, an unknown factor deemed sufficient to abandon a functioning research facility. One of the final detailed entries referenced a brief loss of communication between surface instruments and the lower sections of the borehole, followed by a restoration of signal that produced readings described only as non-standard. The lack of elaboration in this portion of the log stands in contrast to the otherwise meticulous documentation, suggesting either a failure to interpret the data or a decision not to record its specifics. In scientific reporting, particularly in environments as controlled as Antarctic research stations, such omissions are rare, raising questions about what was observed during those final moments of data transmission. The evacuation itself was executed within a narrow time frame, with personnel reportedly leaving behind equipment that, under normal circumstances, would have been secured or retrieved. The Antarctic environment does not allow for casual abandonment. Every tool and instrument represents significant logistical effort and cost, transported across vast distances under challenging conditions. That these were left behind indicates a level of urgency that exceeded standard operational priorities, reinforcing the notion that whatever was occurring beneath the station was both immediate and unpredictable. In the years following the incident, fragments of the report emerged through declassification processes, often appearing in unrelated archives, or appended to broader datasets concerning Antarctic research. Each fragment aligned with the others in tone and content, forming a partial narrative that, while incomplete, remained consistent in its depiction of a subsurface event that defied easy explanation. Scientists familiar with subglacial environments have acknowledged the existence of unknown variables within these hidden systems, yet none have publicly identified a mechanism that would account for the combination of resistance, irregularity variation, and rhythmic vibration described in the log. The Antarctic continent continues to conceal vast regions beneath its ice, areas that remain largely unexplored despite advances in remote sensing and drilling technology. Beneath kilometers of frozen surface lie lakes, sediments, and geological structures that have been isolated for millions of years, preserving conditions unlike any found elsewhere on Earth. The report, in its fragmented form, does not provide definitive answers, but it does suggest that the boundary between known and unknown in these environments may be far less stable than previously assumed. And somewhere beneath that silent expanse of ice, the record ends not with a conclusion, but with the moment something began to push back. Erased electromagnetic signal records. The discrepancy first appeared in archived Antarctic communications, when previously catalogued electromagnetic entries were found missing from mirrored datasets that had been independently preserved across separate research repositories. At first, the inconsistency was treated as a routine synchronization error, the kind that occasionally emerges in large-scale scientific data systems operating under extreme environmental conditions. Yet the files in question were not isolated or corrupted in the conventional sense. They had been deliberately replaced with standardized null entries, as if the original signals had never existed within the recorded timeline. The significance of this only became clearer when cross-comparison revealed that the missing data aligned with a broader pattern of declassified material that has, in fragmented form, been associated with unexplained subsurface activity beneath Antarctica, though no official document explicitly connects these datasets into a single explanation. Simultaneous monitoring logs from polar observation systems recorded brief electromagnetic fluctuations that did not correspond with any known atmospheric or solar activity models at the time of recording. These systems, designed to track geomagnetic disturbances caused by solar wind interactions with Earth's magnetosphere, operate with high sensitivity to ensure even minor variations in ionospheric behavior are captured and categorized. The signals in question, however, exhibited no correlation with recorded solar events. nor did they match patterns typically associated with auroral activity observed in polar regions. Instead, they appeared in short, irregular bursts that registered across multiple independent receivers, suggesting a source that was either unusually localized or distributed in a manner not accounted for by existing geophysical models. Polar communication frameworks operating under standardized scientific coordination protocols rely on layered redundancy between satellite relays and ground-based receivers, yet certain archive files show inconsistencies between these synchronized layers. In a system designed specifically to prevent data loss in remote environments such as Antarctica, redundancy is not optional but foundational, ensuring that if one transmission path fails, others preserve the integrity of the recorded information. The presence of mismatched records across these redundant layers therefore suggests not a failure of transmission, but a divergence in what each layer ultimately retained. This divergence becomes particularly notable in cases where ground-based logs preserve trace signals that no longer appear in satellite-backed archives, raising questions about whether the discrepancy originated from technical error or post-recording modification. Metadata preserved within early-stage exports of Antarctic monitoring reports indicates valid signal acquisition timestamps that no longer align with the content of the currently accessible versions of those same records. In several instances, timestamp sequences remain intact even where waveform data has been removed, creating a structural imbalance between temporal markers and their corresponding signal content. This kind of inconsistency is rarely seen in standardized scientific archiving, where metadata integrity is typically preserved alongside raw observational data. The persistence of these timestamps, despite the absence of their associated signals, implies that the original recordings were once complete and were later altered without full removal of their structural footprint. Before these inconsistencies were identified as anomalies, several of the same entries were initially classified under provisional diagnostic labels used in Antarctic monitoring systems for unverified electromagnetic disturbances, a category typically reserved for signals that exceed baseline environmental noise thresholds without matching known geophysical or atmospheric sources. Internal tagging conventions within early-stage processing logs show that these readings were not dismissed outright, but escalated into review queues intended for cross-agency validation, indicating that the signals met minimum criteria for significance, rather than being treated as background interference. The presence of these classification markers in early exports, later absent from consolidated archives, introduces an additional layer of removal that extends beyond raw waveform deletion into the reinterpretation of how the data was originally understood. Repeated alignment in the timing of deleted electromagnetic anomalies suggests a structured recurrence that becomes more apparent only when filtered against long-term continental observation datasets. These anomalies do not appear randomly distributed across the recording timeline, but instead cluster within specific intervals that correspond with periods of heightened subsurface research activity across Antarctica's ice-covered regions. While no direct causal link is documented, the recurrence pattern is statistically unusual enough to draw attention within comparative analysis frameworks used to identify long-range geophysical trends. The consistency of this alignment across multiple independent datasets raises the possibility that the signals were not isolated disturbances, but part of a repeating phenomenon that was systematically recorded and later removed. Independent Antarctic research programs maintaining parallel environmental monitoring archives show partial retention of waveform traces that do not appear in consolidated international data summaries. These discrepancies persist even in datasets governed by shared scientific coordination agreements, where environmental data is typically exchanged to ensure comprehensive global coverage of polar activity. The existence of waveform traces in one archive but not another suggests that the divergence occurred after initial data sharing, during later stages of consolidation or review. In several cases, archival revision logs indicate that updates were not applied uniformly, with some repositories receiving corrected datasets earlier than others, creating brief windows in which conflicting versions of the same signal coexisted across different systems before stabilization protocols were completed. Later classification updates applied to the affected time windows replace specific signal references with generalized noise indicators, effectively dissolving earlier distinctions between confirmed detection and unverified disturbance. This form of reclassification does not remove the data entirely, but instead redefines its interpretive category, shifting it from structured signal to background interference without preserving the original analytical context. In doing so, the archival record retains the appearance of completeness while obscuring the nature of what was originally observed. The result is a dataset that remains technically intact but narratively incomplete, offering no indication of why the reclassification occurred or what criteria justified the alteration. Isolated fragments preserved in legacy backup systems continue to display waveform structures that resist categorization under established geomagnetic or ionospheric disturbance classifications. These residual traces are incomplete, often truncated mid-pattern, yet they retain enough structural coherence to suggest intentional modulation rather than random environmental noise. Their persistence across disconnected storage systems indicates that they were once part of a broader, continuous data set that has since been fragmented through successive layers of archival revision. Despite repeated attempts at normalization, these fragments continue to reappear in forms that do not fully conform to any recognized electromagnetic behavior model currently used in polar research. Yet the earliest surviving fragment in the unaltered archive still carries a single continuous trace that was never fully removed from the system's lowest redundancy layer. Deep drilling reports marked incomplete. Deep ice drilling operations conducted across Antarctic research programs have historically followed strict stratigraphic documentation standards that record each stage of descent from surface accumulation layers to the deepest recoverable ice cores without interruption. These operations are not experimental in nature, but part of long-standing scientific efforts to reconstruct Earth's climate history through layered ice analysis, a methodology that has produced some of the most detailed atmospheric records available to science. In regions of East Antarctica, where ice sheets can exceed 3 kilometers in thickness, drilling projects are designed to proceed with mechanical precision, ensuring that every meter of penetration is logged, analyzed, and preserved within standardized reporting frameworks. It is within these highly controlled systems that the existence of incomplete drilling records becomes significant, not because interruption is expected, but because it is explicitly designed to be avoided. Standard drilling profiles through Antarctic ice sheets reveal a predictable transition sequence from loosely compacted firn to dense glacial ice, a structure that allows researchers to reconstruct atmospheric conditions spanning hundreds of thousands of years. This layered formation preserves trapped air bubbles, particulate matter, and isotopic signatures that serve as time capsules of Earth's climatic evolution. As depth increases, the physical properties of the ice change in measurable and consistent ways, allowing instrumentation to calibrate itself against known density gradients. Under normal conditions, this progression continues uninterrupted until the basal interface is reached, where ice transitions into either sediment, liquid water, or bedrock depending on local geography beneath the ice sheet. Borehole instrumentation used in deep ice penetration projects is designed to maintain continuous telemetry on pressure, temperature, and core integrity, ensuring that even minor deviations in subsurface resistance are recorded in real time. These systems are engineered with redundancy to prevent data loss, particularly in extreme environments where retrieval opportunities are limited once equipment descends beyond critical depth thresholds. In most documented cases, telemetry remains stable even under increasing pressure conditions, with gradual variations providing expected feedback on changing ice composition. The consistency of these readings is what allows researchers to distinguish between natural structural variation and mechanical interference during drilling progression. As drilling operations approach the interface between ice and underlying bedrock, recorded datasets typically reflect gradual changes in material density, marking the final measurable stage of ice sheet stratigraphy before geological transition. This boundary, often referred to as the basal interface, represents one of the least directly observed regions of the planet due to the technical difficulty of maintaining stable boreholes at extreme depths. In well-documented Antarctic surveys, this transition is usually identifiable through increased resistance, changes in core recovery consistency, and shifts in drilling torque. It is a stage where the physical environment becomes less predictable, yet still conforms to known geological behavior models. In several archived drilling sequences from Antarctic campaigns, minor deviations in core extraction continuity appear near maximum depth thresholds, though these irregularities are usually attributed to equipment stress or localized ice deformation. Such deviations are not uncommon in high-pressure drilling environments, where thermal gradients and mechanical strain can affect both instrumentation and sample integrity. However, these anomalies typically remain minor and are resolved through recalibration or controlled extraction adjustments. The significance of the records in question lies not in the presence of deviation itself, but in the way those deviations precede a more abrupt and unexplained cessation of recorded data. At certain recorded depths approaching multi-kilometre penetration ranges, some drilling logs indicate unexpected resistance patterns that do not correspond precisely with either solid rock contact or standard sedimentary transition zones. These readings are notable because they fall outside the expected range of known subsurface material behaviour, yet they are not accompanied by any documented mechanical failure that would normally explain a halt in operation. In typical drilling scenarios, unusual resistance prompts diagnostic procedures rather than termination, suggesting that continued progression would normally follow unless external factors intervened. The absence of such follow-up procedures in the surviving records introduces a discontinuity between expected operational response and what is actually preserved in the dataset. Within select datasets preserved under Polar Research documentation standards, drilling records terminate mid-sequence without completion of final extraction notes, leaving the progression of borehole advancement partially unaccounted for in the official archive. The interruption is not accompanied by a formal shutdown report, equipment failure summary, or environmental hazard declaration, all of which are standard components of Antarctic drilling documentation when operations cease prematurely. Instead, the records simply end, as though the logging process itself was cut off at the exact moment when continuation would normally be expected. This form of incompleteness is structurally unusual in scientific reporting, where even failed experiments typically preserve a traceable endpoint. In consolidated Antarctic research summaries governed under the Antarctic Treaty System, these incomplete drilling reports are retained only as partial datasets, with final operational stages absent from publicly accessible versions despite evidence of continued system activity beyond the last recorded entry. The governance framework overseeing Antarctic research emphasises transparency and shared scientific access, particularly for environmental and geological data collected in internationally coordinated projects. Yet, in these cases, the absence of final stage documentation persists across multiple repositories, suggesting that the incompleteness is not isolated to a single institution or program. The result is a fragmented historical record in which the beginning and middle of drilling operations are preserved in detail, while the conclusion remains uniformly absent. Analysis of the surviving data fragments indicates that in the final recorded intervals, drilling systems were still functioning within operational parameters prior to the abrupt termination of logs. There is no consistent indication of catastrophic equipment collapse, borehole instability, or environmental evacuation protocols that would typically accompany a sudden end to deep drilling activity. Instead, the telemetry suggests continued mechanical stability up to the last measurable point, reinforcing the unusual nature of the recording gap. The absence of a defined failure event distinguishes these cases from standard operational interruptions and places them in a category of unexplained procedural discontinuity. Across multiple archived drilling programs, the pattern of incompleteness appears not as a single isolated occurrence, but as a recurring structural feature of the deepest penetration attempts recorded in Antarctic ice. While each dataset varies in location and operational context, the point of termination consistently aligns with extreme depth thresholds where subsurface conditions become least understood. This repetition does not establish causation, but it introduces a persistent anomaly within the broader body of Antarctic drilling literature, one defined not by what was discovered, but by what was never fully recorded. In the deepest surviving fragment of the drilling record, the final measurement halts before any confirmed contact with what lay beneath the ice could ever be formally documented. Cross-decade pattern analysis in released data. When consolidated Antarctic research datasets spanning multiple international programs are merged into unified analytical frameworks, previously unnoticed irregularities begin to emerge across records that were never originally intended to be directly comparable. These datasets originate from decades of polar exploration conducted under varying technological standards, yet when aligned within modern comparative systems, certain structural consistencies begin to appear in places where variation would normally be expected. The declassified file that suggests something may have been living beneath Antarctica is not referenced directly in most of these compilations, yet its implications linger in the background of comparative analyses where anomalies begin to cluster in ways that defy isolated interpretation. What makes this level of review significant is not a single observation, but the repetition of similar distortions across entirely separate scientific eras. Long-range compilation of polar expedition materials reveals that certain environmental and geophysical measurements retain structural similarities across decades, even when collected under fundamentally different technological conditions and research methodologies. Early Antarctic expeditions relied heavily on analog instrumentation, manual recording, and limited sampling resolution, while later missions incorporated satellite-linked telemetry, digital modelling systems, and automated environmental tracking. Despite these advancements, the underlying anomaly structures within specific datasets do not shift in proportion to technological improvement, which is unexpected in fields where resolution changes typically alter the appearance of recorded irregularities. Instead, these anomalies appear to persist in a form that suggests continuity independent of instrumentation evolution, raising questions about whether the source of variation is external to measurement systems themselves. Successive generations of Antarctic observational systems, ranging from early analog recording instruments to modern digital telemetry networks, produce datasets that are expected to vary significantly in resolution, yet certain anomaly structures persist with unusual consistency. In most scientific disciplines, improvements in measurement precision lead to refinement of observed patterns, often breaking large irregularities into smaller, more detailed components. In this case, however, the structural shape of specific anomalies remains intact even as the granularity of data increases, as though the underlying phenomenon is being recorded at different levels of clarity without changing its fundamental signature. This consistency across instrumentation eras introduces a paradox within the analytical framework, where increasing precision does not dissolve ambiguity, but instead preserves it in recognizable form. In retrospective alignment of independently archived expedition records, recurring deviations appear only after temporal boundaries between separate research eras are removed during comparative processing. This method of analysis, which integrates datasets across decades into continuous sequences, is typically used to identify long-term environmental trends such as glacial movement, atmospheric composition changes, and oceanic temperature shifts around the Antarctic perimeter. Yet within these broader climate-focused reconstructions, certain deviations emerge that do not correspond to known environmental cycles or predictable geophysical variations. These deviations become visible only when the datasets are treated as continuous rather than isolated, suggesting that their significance may lie not within individual expeditions, but within their accumulated relationship across time. Across multiple historical datasets, identical anomaly structures are assigned different interpretive classifications depending on the scientific period in which they were recorded, despite exhibiting no measurable change in their underlying recorded characteristics. Earlier documentation tends to categorize these irregularities as instrument calibration errors or environmental noise, while later datasets often reclassify similar patterns under broader diagnostic categories that emphasize uncertainty rather than correction. This inconsistency in classification introduces a layer of interpretive drift, where the same structural data is understood differently depending on the prevailing scientific framework of the time. The result is not a change in the data itself, but a shifting perception of its meaning across decades of analysis. Aggregated analysis of polar environmental measurements collected over extended timeframes indicates that certain irregularities recur at intervals that remain consistent even when normalized against shifts in instrumentation, sensitivity, and calibration standards. These intervals do not correspond to known seasonal, orbital, or climatic cycles, nor do they align with documented geological or atmospheric events that typically influence Antarctic environmental systems. Instead, the recurrence appears embedded within the data itself, independent of external environmental drivers that would normally account for repetition. This persistence suggests that the anomaly is not episodic in nature, but structurally embedded within the broader dataset as a recurring feature across time. Independent national Antarctic research archives, when compared under synchronized analytical conditions, reveal overlapping anomaly windows that appear across separate observational infrastructures with no documented operational interdependence. These infrastructures were developed independently by different scientific programs, often separated by geography, funding, and methodological design, yet the alignment of specific irregularities occurs within overlapping timeframes that cannot be easily attributed to coordinated measurement activity. In standard comparative analysis, such overlaps would typically indicate shared environmental triggers or synchronized observational focus, yet no such common variables are present in these cases. The alignment therefore exists without an identifiable mechanism of synchronization, creating a structural correspondence that emerges only through cross-referential study. When reconstructed datasets derived from legacy Antarctic archives are processed through modern normalization tools, certain anomaly signatures persist even in cases where original raw files are incomplete or partially degraded. In these reconstructions, the same irregular structures reappear despite the absence of full source continuity, suggesting that the pattern is not dependent on a single intact dataset, but is instead recoverable through multiple independent reconstruction pathways. This resilience to data loss introduces an additional layer of complexity, as it implies that the anomaly can survive standard archival degradation processes that typically eliminate or smooth out inconsistencies over time. Further comparative review of long-term polar datasets reveals that certain regions and time windows are repeatedly excluded or labelled as statistically insignificant by independent research teams operating across different decades. However, when these excluded segments are reintroduced into unified analysis frameworks, they consistently align with the same structural anomalies observed elsewhere in the dataset. This repeated convergence of non-significant classifications suggests a systematic blind spot that persists across methodological generations, rather than a true absence of meaningful data, reinforcing the idea that interpretive thresholds themselves may be shaping what is considered visible within Antarctic research outputs. Within the most recently harmonized global Antarctic datasets governed under the Antarctic Treaty System, the same structural anomaly signatures continue to appear unchanged, despite full transitions in data collection technology and analytical frameworks. These harmonized datasets are intended to resolve inconsistencies between national research outputs by standardizing formatting, calibration references, and interpretive categories across all contributing programs. However, even after normalization processes are applied, the recurring anomalies persist in identical structural form, unaffected by adjustments intended to eliminate cross-system variation. This persistence across harmonized frameworks suggests that the anomaly is not an artifact of data collection or processing, but a feature that survives every attempt at analytical reconciliation. Even in the most recent unified dataset revisions, the recurring pattern remains identical in form, as though time itself has never altered what the records are repeatedly showing. The final declassified transmission. Reassembled communication fragments attributed to the final Antarctic operational channel emerge only through overlapping satellite relay buffers, where incomplete message sequences have been reconstructed from partially synchronized reception nodes. In practical terms, Antarctic communication systems rely on a layered relay architecture in which transmissions pass through satellite links, regional ground stations, and intermediary storage buffers before being consolidated into archival records, meaning that even a single operational message can exist simultaneously across multiple incomplete nodes before final synchronization occurs. The declassified file that has been circulated among fragmented archival releases, often cited in broader discussions suggesting anomalous activity beneath Antarctica, is referenced only indirectly here through its final communication trace, which survives not as a complete record but as a reconstructed sequence assembled from discontinuous transmissions. Unlike structured scientific reports or environmental datasets, this material does not exist as a finalized document but as a layered reconstruction of a communication stream that was never formally concluded, preserved only through partial redundancies embedded within global relay systems. The significance of this reconstruction lies not in what was recorded, but in the moment the recording itself ceased to maintain continuity. Field communications within the recovered transmission begin with standard operational reporting, detailing environmental conditions, system stability, and routine procedural confirmations consistent with established Antarctic expedition protocols. References to weather conditions, equipment status, and logistical coordination appear in the expected format used across polar operations, where clarity and brevity are essential due to limited transmission windows and unstable connectivity. In the early portion of the sequence, the communication maintains full structural integrity, suggesting that the transmission originated under stable conditions with no immediate indication of system failure. At this stage, nothing within the content deviates from the established norms of Antarctic field communication, which typically prioritizes environmental reporting and operational status updates in structured, predictable intervals. Intermittent degradation in the recovered audio text stream becomes detectable as minor distortions in sentence continuity, suggesting fluctuations in relay integrity rather than immediate system failure. High-latitude communication systems operating in Antarctic regions are known to be affected by ionospheric variability, particularly during periods of heightened solar interaction with Earth's magnetic field, which can introduce temporary disruptions in signal clarity. These disruptions typically manifest as brief delays, partial sentence loss, or minor distortion in transmission fidelity, all of which are consistent with environmental interference rather than structural system breakdown. However, in this reconstructed sequence, the degradation does not follow a uniform pattern, instead appearing in uneven intervals that complicate straightforward classification of the interference source. Across multiple relay nodes, the same fragments arrive with slight temporal offsets, requiring post-reception reordering to restore approximate continuity, yet even after alignment, certain segments remain out of sequence in a way that resists full temporal stabilization. Progressive fragmentation within the transmission sequence introduces repeated partial restarts of identical phrases, indicating attempts at message correction or retransmission under increasingly unstable communication conditions. Such repetition is often associated with automated systems attempting to re-establish clarity after packet loss, a common occurrence in remote polar communication networks where signal stability can fluctuate rapidly. Yet the repetition in this sequence appears less like automated correction and more like incomplete restoration of interrupted thought, where phrases are initiated but never fully resolved into complete operational statements. This shift marks a transition from environmental instability to communicative breakdown, though no formal failure declaration is recorded within the surviving fragments. Within polar communication systems operating at extreme latitudes, ionospheric variability is known to disrupt high-frequency transmission channels, yet the recorded distortions in this sequence do not conform uniformly to expected propagation interference patterns. Normally, such interference produces recognizable signal degradation profiles that can be accounted for through redundancy filtering or retransmission protocols, ensuring that critical operational data remains recoverable. In this case, however, the distortions affect structural continuity rather than simple signal clarity, resulting in incomplete message formations that resist full reconstruction even after buffer alignment. The irregularity of this disruption introduces ambiguity into whether the interference originates from environmental conditions alone or from an as-yet unclassified transmission failure mode. Structural coherence within the message begins to degrade as complete operational statements are replaced by truncated segments that fail to resolve into finished procedural reports. Standard Antarctic operational communication relies on precise, complete phrasing to ensure safety and coordination in isolated environments where miscommunication can have significant logistical consequences. The presence of incomplete statements suggests that either the transmission source was unable to maintain full, cognitive or mechanical continuity in message construction, or that the communication channel itself was losing the capacity to preserve full data packets in sequence. In either case, the result is a progressive erosion of message integrity that moves beyond simple interference and into sustained fragmentation. In the concluding portion of the reconstructed feed, overlapping fragments suggest simultaneous transmission attempts from a single source that can no longer maintain continuous communication output. This phenomenon appears as layered partial sentences that begin at identical structural points but diverge before completion, as though multiple attempts at transmission are being initiated without successful termination of prior sequences. In standard communication systems, such overlap would typically indicate buffering failure or synchronization error between sending and receiving nodes. However, the persistence of this pattern across multiple successive fragments suggests a deeper breakdown in transmission continuity, rather than isolated technical malfunction. Within the final buffer extraction, the communication stream ceases without recorded shutdown protocol, termination signal, or subsequent re-establishment attempt across any connected relay system. Antarctic operational procedures typically require explicit termination sequences for field communications, ensuring that all transmissions are formally closed and archived with complete metadata for later review. The absence of such closure in this case is structurally significant, as it leaves the communication event without a defined endpoint, existing only as an incomplete sequence suspended in archival reconstruction. No follow-up transmission appears in any synchronized relay system, and no secondary confirmation of shutdown is recorded within the broader communication network. The last recovered fragment ends before the final instruction is completed, leaving the transmission permanently suspended at the exact moment it stops speaking.